Thanks for coming, everyone. Welcome to the next iteration of the Updates in Cooperative AI seminar series. We've got Max Kleiman-Weiner here to talk to us in just a second. Before Max's talk, I just want to very quickly highlight a few things. So just a quick little bit of advertising. So if my slides advance. The main one I just want to mention is that some of you might have already seen, but just a few days ago, the call for applications for the new iteration of the Cooperative AI PhD Fellowship went out. So that is open until the middle of November, 16th of November. You can see some of the things there that the fellowship provides people with. So a bunch of research support, so conference and compute budgets, loads of opportunities to collaborate with people in the Cooperative AI network, and of course, a big living stipend as well to support you. So yeah, this is available to enrolled students or students who expect to enroll in the coming academic year. So that's the 2026 academic year. And so people who might be preparing applications around now or towards the end of the year. So yeah, if you're not already aware of this, then yeah, do consider it. Do also forward it on to people who you think might have missed it and might be good candidates. Cool. I think that's mainly the only thing I wanted to mention. For those of you who haven't come to this seminar series before, this is our regular monthly seminar series. There's a few that have already gone. You can find the recordings on YouTube. In general, the focus here is on some kind of bigger picture ideas and methodologies and ways of thinking about cooperation problems in the context of advanced AI agents, new cutting edge results. So some of the things that Max is going to be talking about is from a recent paper of his, and also plenty of time for critical discussion of those ideas and that it will be presented. So I'll hand over to Max in just a second, but we'll have around, I think, about 40 minutes of presentation and then 20 minutes at the end for questions and discussion. During the talk, please do use the Q&A function in Zoom to ask any questions you might have. And then at the end, for the discussion period, I will MC. And if you are able to turn on your camera and mic and ask questions, I'll basically call on people in terms of which questions are most upvoted. And if you're not, then I'm happy to read out questions and forward them on to Max. And then, yeah, hopefully we'll have time for plenty of lively discussion there. Okay. So those are all the announcements I wanted to make. So without further ado, then I'm very, very pleased to be able to introduce Max. So Max Kleiman-Weiner is an assistant professor at the University of Washington and the PI of the Computational Minds and Machines Lab. His goal is to create computational models that explain how the mind works and draw on insights from how people learn, think, and act to build smarter and more human-like artificial intelligence. He did his PhD in computational cognitive science at MIT, where he received fellowships from the Hertz Foundation and the NSF. And he's also founded two AI companies, Common Sense Machines and Diffio. So yeah, Max is a kind of longtime friend of the Cooperative AI Foundation, has done loads of great work in this space. So very excited to hand over to him now. And yeah, thank you for joining us, Max.
Awesome. Thank you so much for the intro. And I'm happy to see a few familiar names and in the Zoom audience. So great to see you all. All right, I'll get started. So today I'm going to talk about this recent work evolving general cooperation with the Bayesian theory of mind. And it's for those of you who are used to the standard computer science publication cycle, this is a project that I started back in 2018 and was just published this year. So you can kind of do the math of the gap it takes to do some things in academia. All right, so let me just sort of jump into this. And I like to start off with the observation that cooperation behaviors are really ubiquitous across the animal kingdom, right? So here's an example of ants, and they're working together to basically create this bridge through the air, right? So that they can cross and take a shortcut from the branch to the leaf without having to go all the way around. Now, no individual ant could close that gap, but when they work together, they can. And here are wolves that are working together to hunt a kind of a larger prey animal that is bigger than any of them on their own, but if they work together, they can figure it out. And then today, as we're faced with machine intelligence, new forms of cooperation become possible, right? Cooperation between humans and between machines and humans and machines. And when I first put these slides together, it seemed like the kinds of cooperation that we would be expecting to see are ones in this kind of robotic way where we would have real agents that are interacting in the physical world. And of course, the kinds of agents that we are now tasked with cooperating with look very different and look much more like a chat window. And if there's time, we can discuss that a little bit at the end. But I think in still many ways, with all of the different kinds of cooperation we see in the animal kingdom and even in AI, human cooperation is still distinct. So here's an example of a young child, a nonverbal infant. I'm sure many of you have seen this video before. And the experimenter, Felix Wernicke, kind of signals his intention just through his action. There's no communication. And the young child, kind of without any prompting, gets up and fulfills his intention. And so this is a kind of cooperative sophistication that is like kind of unbelievable. Just by 18 months, we have this kind of ability to exceed all non-human intelligences in a domain like this. 3-year-olds can go even further. They can negotiate how to divide the fruits of their labor fairly, and 5-year-olds can solve many different kinds of social dilemmas using things like turn-taking rules and general norms. And actually, at a recent kind of lab gathering, I had one of my grad students, and this is my son and my wife Natasha. We tried to replicate this study. So here's KJ, our student, and he's bumping into the cabinet, and here comes the 19-month-old. He goes and he opens the drawer for him. So maybe not always nice to see scientific replication. I will say though that he needed a little bit of hey help. So it wasn't fully nonverbal, but so maybe the intention recognition was there, but the motivation to help maybe was still developing. Okay. But I think in many ways, all of these very early developing abilities are just the prelude to the unprecedented levels of cooperation that we see that underlie things like social contracts, businesses, government, science, and technology. In many cases, these achievements are the work of millions of unrelated individuals that are in different locations that may never meet. And so really I want to understand what the origins of these abilities are. What's the cognition that underlies this kind of intelligence that helps distinguish us from other animals? And then how can we use that kind of better scientific understanding to then ultimately build machines or AI systems that are equally capable and equally aligned with our own abilities and with humans more broadly? Okay, so I'd like to start off just with like kind of setting what the challenge is, right? So, based on what I've just shown you, cooperation is great. It's this amazing force, but it's also a real challenge. And the starting place for this is like, well, yeah, collectively we'd all be better off if we cooperate, but an individual might be better off if they're looking out only for themselves, right? And so this idea has sometimes been termed like the tragedy of the commons. Just to give an example, right? I'd love to. I get all the great benefits from the government, right? They provide roads and all kinds of services, but I have to pay into that. I pay my taxes. Now, if I didn't pay my taxes, that'd be even better, right? Because I'd get to use all those benefits, but I wouldn't have to pay any tax money to the government. Well, if everybody applied that same logic, or if everyone stopped paying their taxes, there'd be no collective benefits to distribute to all of us, right? So there's this fundamental tension about what's good for the group and what's good for the individual. And we want to figure out how to reconcile that tension, right? This tension kind of goes against the logic of evolution, which is about individual selection. And it also goes against the logic of economic rational agency, which is the idea that people and AI agents to some extent are rational actors that are trying to maximize their own payoffs, right? And so I'm certainly not the first to tackle this problem. It may be in many ways a central pursuit of many different fields, and in particular the field of evolutionary game theory and multi-agent systems for almost 40 plus years, maybe 50 now. Okay, so let's kind of dive in a little bit deeper. I think one way to study this, and I'm going to assume that people are somewhat familiar with things like the prisoner's dilemma, but I'll just give a very, very brief account of it, right? So I like these kinds of games because you can almost think of them as like a kind of Drosophila of this tension, right? This tension between what's good for the group. So in a game like this, there's two possible actions. You can either play the action cooperate or you can play the action compete. And if both players play cooperate, they both get 7 payoff of 7, right? So you can look through this and basically if all the different possibilities of actions, 7/7 is what's best for the group, right? That gives 14 in total welfare. But then if you look more closely, you say, well, no matter what the other person plays, if I'm the row player, I'm better off playing compete no matter what the other player plays, right? So if the other player plays cooperate, well, I could either get 7 or I could get 8, so I should play compete. If the other player plays compete, well, I either get -1 or 4, so I should play compete, right? And so this logic of trying to figure out what's best for yourself kind of takes you from what's best for the group to picking this much more individualistic and ultimately less socially beneficial action, right? So how do we solve this? Okay, so there have been many solutions to this problem over the past, now 40 years. One of the most famous is to say, well, okay, we're not going to just play that game once. We're going to actually play a repeated version of this game. So we're going to have the game be played many times. So, we play once, then we play, see what happens, play again, and so on. And when you play in a setting like that, this was a famous tournament run by Robert Axelrod, you see a strategy emerge called tit for tat. And the tit for tat strategy is so popular and famous because it's so simple. So the idea underlying tit for tat is that you start off cooperate, and then after that, you just copy whatever the other player previously played. So I start off being by cooperative, the idea, be nice at first. And then if they cooperate with me, cooperate back. If they compete with me, compete back, right? So this very basic idea of reciprocity. And I think, that's led to all different forms of reciprocity. I'm going to talk about them later on in this talk. But I want to just highlight, I think, a kind of key underlying issue with a strategy like tit for tat, when you think about it from either cognitive or even from an AI perspective, which is that to the extent that tit for tat corresponds to something related to reciprocity, is very much just whether or not we see reciprocity in its behavior. Right? There's nothing in this strategy that says anything about cooperation. In fact, the strategy doesn't even look at the payoffs of the game, right? It just knows play action ID number 1, and then play the action ID number of the other player if they played. Now, if the game's asymmetric, that might not make any sense, right? Like you might not want to do that to cooperate. It doesn't have any notion of what's good for the group or good for a particular individual. It just knows what actions to play and when. That's it, right? And so I think we can see like the human concept of tit for tat in particular, and reciprocity in general, is going to be much richer than what these kind of simple strategies, as represented as finite state automata, are going to be capable of representing. And so if we want to actually apply this stuff in the real world, we're going to need to think about how to think about like scalable and ultimately, as I'll show, more robust versions of this. Now, the problem gets somewhat worse when you start to think, well, what happens if I'm not playing the prisoner's dilemma? Or what if I change the game in many of a variety of ways? And I'll, again, talk about these in later on. But the problem becomes even worse. You can kind of see in the bottom right, what's basically happens is that researchers have then discovered this like zoo of different autonoma, which is, oh, well, this one's good for this scenario, and this one's good for that scenario. And when you're doing indirect reciprocity, play this one. And when you're doing stag hunt, play this one. And so, what's the cumulative result of this is that we don't have a single theory that explains reciprocity in a more abstract or general way. Instead, we just have simple point solutions to particular problems. Now, it's unlikely, I think, that the human mind has learned new algorithms for every different kinds of social problem that it has faced. And unlikely also that we're going to be able to hand engineer those kinds of solutions for AI. I think it's much more likely that we have a much more general and abstract notion of these concepts like cooperation and reciprocity that we can then apply flexibly and broadly. Okay. So my goal to reverse engineer human cooperation, and this project is really trying to get it kind of two pieces. Try to understand the cognitive processes that underlie social intelligence and how they contribute to the scale and scope of cooperation. In this talk, I'm going to spend most of the time talking about basically the power of theory of mind as a kind of ability of understanding the latent states that other minds have and understanding other minds as agents and a particular way of formalizing those ideas. And then second, how can we build super AI that's a super cooperator, right? Use to design cooperative artificial intelligence that can actually interact with us in the kinds of general scenarios that we operate in. Before going into that though, I sometimes realize for the AI, for like a more AI audience, it's important to answer this question. And I think the cooperative AI folks in the remote need this motivation, but why are we studying self-interested AI at all? And I think, there's a lot of reasons to think about this question, but or ways of thinking about this question. Many have taken the form of like, well, we don't know what AI is going to be aligned to, or AI is going to have self-interest. It has, certain desires that are going to be present in any goal-seeking behavior. But I think there's actually a bigger reason that's actually much more pragmatic that we're actually grappling with even today with today's systems, which is that AI systems are not going to operate especially they're already not operating just as like ChatGPT and you interact with the company, or Anthropic and you interact with the company's AI agent. We're starting to deploy agents where those agents are representing particular companies, particular individuals. And for those agents to be effective as delegates, they actually have to be somewhat self-interested, right? So like if I want to give my web agent access to be able to actually do accomplished tasks for me online, it needs to have access to my credit cards and bank accounts. Now that means when someone says, "Hey, can you just like help me out and make a donation, or can you just like, pay a little bit extra? I really appreciate it. Like, I don't want it to be too cooperative. I want it to be self-interested and be cooperative in ways that lead to mutual benefit, ways that are beneficial for, ideally for both parties, but especially for me, if it's my money and I'm not even there to make the donation myself, right? Okay, so I think we're already seeing the AI agents that are being deployed with the assumption that they are going to act in self-interested ways, and that's what we want them to do. And I think this was really nicely highlighted in this like Project Vend demo from Anthropic, where they basically set up a vending machine in their office and had Claude run the kind of business of the vending machine. And what basically happened is it didn't work well at all, right? So like here's the like net worth of the vending machine over time. It just like starts plummeting. And what happened was is that like it's just too nice, right? Like people would say, well, that's just a little bit too expensive. Can you just like give it to me for cheaper? And ask it 3 times. It's like, okay, fine, yeah, you can have it. You really want it, right? And so that's not the kind of AI that's going to actually be able to be successful in the kind of scenarios that we ultimately want these systems to operate in, right? So just broad helpfulness is not necessarily the right goal. Self-interest is potentially an important feature of having large language model agents actually be useful for us. So given that, we need to understand how to get them to cooperate with each other and with us. Okay, so a little bit of motivation there coming from the AI angle, and this is something I'm also hoping to follow up on in future work. So if you're interested, please reach out. Pitched this many times, no one's working on it yet. So if you are interested, please talk to me. Okay, so back to evolution of cooperation and how do we get to cooperation? So unlike this prior work, which looked at the prisoner's dilemma, we thought, well, we need to start thinking about environments that are much richer and broader, that include a lot more variation than just a single kind of game. That's kind of why everyone got stuck, right? They saw one game and they just developed these single algorithms for those one games. So what we did is we developed what we call the game generator. And the idea is that the game generator produces many games, and that could be solved by many different strategies. Okay, so the idea is that it's basically a probabilistic generator of possible game theoretic scenarios. Each sample from the game generator looks something like this. I'll give you a flavor. So you sample the players, so it doesn't have to be 2 players, it could be more. You sample the costs and benefits of each action. You sample the number of actions, so it doesn't have to be 2 actions, it can be many. And then for each action, you sample the costs and the benefits of that action type. So one example sample would just be like a kind of donation game where you pay one to give a bigger payoff to somebody else. So I here is showing like I pays J, pays 1 to give J a bonus of 3, or they always have the option of just kind of like no op, doing nothing, no payoffs change. Sample 2 is an example of something like a welfare distribution game, right? So J can just give a surplus to either player I or K, or just throw it out, do nothing. And then in the third sample, it's some kind of hybrid, like you can pay a little bit more to give an even bigger bonus to somebody, or pay a small amount to give still a proportionally bigger bonus to somebody else, and all the different variations that this can create, right? So within this game, there are things like prisoner's dilemma, allocation games, and I think it's unrealistic to imagine that each of these samples is going to be optimized by a different algorithm, right? So this kind of already is trying to prove our point that we don't think people are going to play these games using kind of a different strategy for every sample. It's going to require something more abstract. Okay. So if we started off with the problem was the iterated prisoner's dilemma, and the solution we got was something like tit for tat, then the kind of natural question I want to ask is, when we start off with this game generator environment, what kind of answer are we going to get, right? What is a solution that enables cooperation in a scenario like this? And so, the first kind of, maybe somewhat obvious, but the first important contribution that we make is that we shouldn't be thinking about strategies. We should be thinking about utilities, and the way we think about integrating the utility of other agents into our own, right? So here's kind of the default baseline. This is like the Homo economicus, right? The selfish agent. Player I just cares about the rewards that they get. Cares about the rewards that player I receives. And then here's another simple version of this, again, kind of built from the behavioral economics literature. Player I cares about the rewards that player I gets, but also cares about the rewards that every other player gets, right? All the other players that you can imagine. And now again, we have to ask the same question we've been talking about, right? Well, which is better? Like, is it better to be, the agent that will get the best outcome when playing against itself, like the altruistic player will? Or is it the player that, does the best when playing against anybody else, this selfish player, right? So, how do we know? And I think the really key insight here is that in the social world, we can't think about optimization against a fixed target. Because what that target is going to depend on the other players in that environment, right? And the social world itself is changing and is adaptive. And so we have to be basically figuring out how that adaptation will happen in order to effectively figure out which of these is going to be more well adapted or more rational from that perspective. So let me give you a quick demo of what I mean. Let's imagine we start out in a world where every agent is playing this altruistic style, right? They're taking everybody's utility and adding it together. Well, they'd have the highest total welfare. That's great. Well, now imagine we introduce just like one selfish player. That guy's going to be doing a little bit better than everybody else, right? Because he can exploit all these altruistic players, but the altruistic players are kind of just giving. They just keep giving and giving, right? And now imagine some kind of cultural or biological evolutionary dynamic where the players that do better are more likely to replicate their values or replicate their utility functions. So over time, more players are becoming selfish. And by the end, we get to what's called an equilibrium state of this system, right? Where all of the players in the population are playing the selfish strategy. Okay, so an evolutionary dynamic is one way of taking account of the way in which the environment itself is adapting to how the players are playing. Now, this doesn't look very good, right? We started with a world where everyone was being altruistic and cooperative, and ended up in a world where nobody was. And this is, an equilibrium of that you get with these two strategies. And I think, but it's important, I think, to say, well, these aren't the only two strategies, right? Natural selection does not forbid cooperation and generosity. It just makes them difficult engineering problems, right? So we have to think about, well, what's the right way to get cooperation in an environment like this? And so the primary contribution of our work is to introduce this new way of thinking about a utility calculus for reciprocity. And let me unpack it. So the Bayesian reciprocator says, take into account your own welfare. So care about, player I cares about RI, their own reward. And they care and they weight the rewards that other players achieve, like the altruistic agent, but they don't do it unconditionally. They weight the rewards of others proportional to their belief that they think that the other player is also a Bayesian reciprocator, right? So it's a kind of similarity or self-recognition based preference, but it's done at the level of the utility calculus itself. And what makes this powerful is that the utility calculus is actually the causal mechanism by which how agents act. You can't fake the value system without adopting the value system. So now, but the challenge of something like this, it would be great, right? If you knew everybody's utility function, you'd be in business, right? But you don't. All you can do is have beliefs about others' utilities. They're not observed. And so this requires what cognitive scientists call a theory of mind, the ability to infer the causal structures inside other people's heads that drive their behavior and to infer them from their actions. Okay, so let me unpack how we're going to go about that. And we're going to use, a relatively, well-known idea for modeling theory of mind called Bayesian theory of mind. And the idea is relatively, hopefully straightforward. The idea says, well, I'm going to assume other agents, depending on their type, are, basically soft maxing their utility function. So given a particular agent's type, I think the probability of them taking a particular action is going to be at least proportional to their utility function. So they're going to take actions that have high utility under their utility function. And so theory of mind, we can just apply Bayes' rule, right? Where the posterior says, well, given that I saw you take a bunch of actions, what utility function do you have? What type of agent are you? And to solve for that posterior, I just have my prior, and then I can take my model of action, this, as the likelihood. And by iterating this over time, I can keep track of, what the likelihood that different agents are of different types just by observing their actions. And I'll show some examples of how this works. Okay, so here's an example. And what I described to you is basically kind of the naive version of Bayesian theory of mind. I'm going to go through the example with the idea of showing you how it works and why it's somewhat intuitive, but why we're going to ultimately have to go beyond it in order to use it in a kind of interactive multi-agent context, which hadn't been done before. Okay. I see there's a bunch of questions in the chat. Okay, cool. We'll get to this at the end. So, okay, so here is the priors that we might have about player A. And I'm going to start by just putting a little bit of a higher prior on the Bayesian reciprocator and then splitting the probability mass over the other two agents, altruistic and selfish. Okay, so, and then we're just going to imagine a simple game just to make it easy to understand what's going on. You can either give to pay one to give three, so you're paying a small cost to have a bigger benefit, or you play keep, you just do nothing. That's the more selfish act. Okay, so player A gives, plays give when playing with player B, right? So how would that, think in your mind, think about what would that do, what's that going to do to these distributions of belief? Well, very unlikely that a selfish player would do that, right? Very possible an altruistic or a Bayesian reciprocator would do that. So we see in our updated distribution much less weight on the selfish agent, and that weight's been moved to the other two types. Likewise, if player A played keep when playing with player B, we would see kind of the opposite. Well, very likely to be a selfish player, because that's the kind of player who would play keep on a first interaction with a prior like that, and very unlikely to be the Bayesian reciprocator, but still possible. Okay, so things look good, right? Now let's play it again, right? So player A has played keep with player B. Here's what we think about player A. That's just copying it from the last slide. Now player B plays keep when playing with player A. So think about what that should do to your beliefs. What, and in particular, your beliefs about B. So if we naively apply that Bayesian theory of mind that I just showed you, what we would find is that, well, B and A are identical. They both played keep when interacting with each other. But intuitively, I hope you have the intuition that, well, A played keep on the first move and B played keep on the second move. And so B might be playing keep not because they're selfish, but to reciprocate, right? B might have his beliefs is that now that A is selfish, and so a Bayesian reciprocator should also be playing keep in that situation. So this probabilistic doesn't really they shouldn't be the same, that's for sure, right? Because B has a lot more information about A than A had about B. Okay, so how can we capture this intuition? Well, the basic idea is that we have to have some kind of recursive theory of mind, a model of others' minds that isn't just about what their mental contents are, but about how their mental contents themselves include models of others' agents' minds, right? So A's models of B and B's models of A, and so on. And you can see how this is going to get very complicated very quickly, right? Because we're going to have to model A, modeling B, modeling C, modeling A. And in fact, any kind of way of doing this kind of unrolling is ultimately a kind of approximation. And that approximation is going to grow exponentially in the number of interactions that are observed. So it quickly becomes intractable. And when we started by approximating these belief updates in this approximation, we found that actually they quickly become unstable, and you get this kind of unraveling effect that happens quite rapidly. Okay. So what we did is we looked at the structure of the game and realized there's some key ideas about common knowledge that we can use to actually structure how beliefs are updated. So instead, an intuitive way of thinking about this is that instead of having agents track what A thinks, B thinks, D thinks, A thinks, you can track what do we know? What does a particular group of agents know together? Okay, so the insight here is that, well, A's models of B's belief should only depend on the events that have been jointly observed by A and B, right? And if an event was observed by A and not B, or was observed by B and not A, it can't be part of A's model of B's beliefs, because if it was observed by A and not B, it would just be irrational, right? Like, how could that be part of the joint belief? The other one player didn't observe it. And in the second case, where A didn't observe it, well, how could it be in A's models of the beliefs? They weren't even aware of it, right? Okay, so all we need to do is condition on this joint subset. And a way to think about this is that under this model, A's models of B's beliefs, you can think of them as being identical to the beliefs that an external agent would have, kind of thinking from a view from nowhere perspective, had they been able to jointly observe what A and B had both jointly observed. Okay. And so this has some nicer scaling properties, right? So instead of having to track, that kind of infinite nesting of beliefs, we can just track what do A and B think, what do A and C think, what do we all think, right? Or what do we all know? And this reasoning really simplifies how we might reason and update knowledge in large groups. And we're doing this in a relatively exact way in this paper, but if there's time in the Q&A, I'd be happy to chat about some ideas I have of approximations to this scheme that can allow for like really scalable ways of doing large-scale belief update by thinking through approximations to common knowledge. I think that's an exciting open question for these kinds of for thinking about these kinds of ideas. Okay, so let's go back to our example, and let's add in this new kind of joint belief calculus into our agents' minds. So you can see, so before we had, this incorrect inference about B. What happens when we change it? Well, we get something that makes a lot more sense. It's still unlikely that B was unconditionally cooperative, like an altruistic agent would be, but it's now much more likely that they're just reciprocal, right? That they wanted to reciprocate in that situation, and they could still be selfish, right? It's probabilistic. They might just be selfish and would have played keep no matter what. I'll just show you another example without the recursive theory of mind, right? When A plays keep and then B plays give after, without that recursive theory of mind, the model predicts that it's likely it could be this reciprocal agent. But we know that should be relatively unlikely, right? So again, apply our recursive model and we get the much more kind of common sense output, which is that if B plays give after A played keep with B, it's more likely that B is just unconditionally nice, right? They're altruistic and they're not likely to be a reciprocal agent. Okay. So I showed you how this worked in like in kind of a few interactions. Let me zoom out and kind of give you the loop of how these agents work. They start with priors over the beliefs of the utility functions others have. They then choose actions. They act by maximizing their utility subject to those beliefs using that utility function that we went over. They observe the behavior in the game, what they played and what everybody else played, what happened. And then they compute the likelihoods of the behavior, right? Given what happened, what's the likelihood that of the actions that each player ended up taking, and then use that likelihood in Bayes' rule to update the models of belief over all the different subsets of agents, and then repeat for every iteration. Okay, so let me show you first within I'm going to show you kind of two kinds of results. Some are within a generation and some are across generations. And within a generation, what we were interested in is what do the learning dynamics look like, right? Can these agents rapidly learn the types of others in the game generator environment? So what I'm showing you is the beliefs of the Bayesian reciprocator when playing against the selfish agent. And what you're seeing are their belief distribution as a function of the number of times they're interacting with that player. And what you should see is very quickly, after just a few interactions, they quickly learn that this is a selfish player. And that's really important, right? You're very fast at detecting who is not a cooperative player. Now, when we pair them with the other types, either themselves or altruistic, it's a little bit less obvious because both are cooperative. But it does, over time, although more slowly, learn, yeah, I'm playing an altruistic player, and the beliefs you can see slowly creeping up there. So this is good news, right? We're able to quickly determine who's selfish and slowly figure out also who's altruistic. Okay. Now let's look at this across generations. We're going to look at a repeated version of the game generator. And so here's the game generator, and I'm going to, just for the evolution aficionados, give you some quick details. I can go back to these if there's interest later on. In each generation, the Moran process is an evolutionary model of how players change types. Under each generation, one player will basically pick to change. That player dies and then is reborn and chooses to a new type based softly on the payoffs of the players in the previous generation. Okay, and we just repeat that kind of in an infinite way. We study this in finite populations, which are more challenging for cooperation. And we study this in the limit of small mutations, which allow us to apply some really powerful analytic tools to really quickly compute the steady state proportion of strategies in equilibrium. Okay. So here's what the output of these simulations look like. What we're doing is, on the x-axis, I'm varying how many times the game is repeated between 1 and 9. And what I'm plotting are the relative distribution of each strategy, each player type, under that number of repetitions. So you can see when the game is not repeated, when it's a one-shot game, that's this bar here, this bar over 1. It's mostly red, right? Because almost all of the agents at a steady state are the selfish type. As we increase the game length, the Bayesian reciprocator, the conditions for reciprocity are possible. And the Bayesian reciprocator becomes the most abundant strategy in the population. And you can see there's a little bit of green here, but the altruistic agent never really gets off the ground. So this is good news, right? The Bayesian reciprocator kind of solves this engineering problem, right? It's able to cooperate in an environment where you're never playing the same game twice. Now, I didn't go into the details here, but it's one real challenge for these automata-like strategies, like tit for tat, is dealing with stochasticity and noise. And the reason for that is that if you think about it as like when you're playing tit for tat, if you are off by one, then instead of playing cooperate, you alternate between cooperation and defection. And so people over the years have come up with different strategies like generous tit for tat or win state lose shift that have different kinds of error correction mechanisms. But if you kind of run the simulations yourself, you'll see these are kind of hacks and they aren't very robust to noise. So robustness to noise is a really important feature of successful cooperation in these environments. So what we did is we looked at that. We added a probability of action error. And what that means is whenever the agent tries to pick an action, there's some probability it just flips to a different action. And what you can see is that, the model is pretty robust. If you add enough noise, well, if you add enough noise, then all the models are sort of equal at a certain point because they're just very noisy. But, our model basically can cut through a lot of that noise and still figure out who is who, even under in a highly noisy environment. And I'll show you where this gets to be even more important in the later study. Okay, and then this is just showing, yes, as you get noisier, as you add more noise, you need to have a longer sequence of games, right? In order for cooperation to be possible. Right? So the intuition there, right, is that noise is reducing the information of each action. And so you need more time to figure out who's selfish and who's not in order to condition your cooperation, right? So that should be relatively intuitive, and that's what we see. And this is just showing, yes, when the Bayesian reciprocator is the dominant strategy, the payoffs in the population are also very high. They're near maximum. So it actually is leading to a cooperative outcome at the end. Okay, so that's the short story for direct reciprocity, meaning, and maybe I should say a little bit more about that. Direct reciprocity, this is a repeated game, but the only players who see what's going on are the players that are involved in the interaction. And so you can think of direct reciprocity as a kind of, I'll help you if you help me, right? I'll cooperate with you if you cooperate back, right? So it's that kind of directly reciprocal interaction. Now, we know many interactions in the real world do not have that flavor. Like in many contexts, you never interact with the same person twice, right? But your actions may be observable to others. Okay, so now we looked at a second setting where you interact with each player just once, but those interactions are public to everybody. And so again, we can look at within a generation, what are the beliefs that players have in a setup like that. And you can see, again, very quickly can learn who is selfish. That's over here, right on the bottom right, where we quickly learn the red converges to 1 in this red column. But maybe interesting to some is that you are actually also able to quickly learn who is altruistic. And that should make sense, right? Because if I see someone defect, and then I see someone else cooperate with that defector, I know they're altruistic, right? So it's easier to get information about unconditional altruism in this public setting than it is in a private setting. Okay. So now let's take this. So this looks good, right? The agents are able to learn who's who within a generation. And now let's look at that across generations in this evolutionary setting. Players only interact in a one-shot way, but information about but here so in the prior literature, people have talked about reputation as a way of solving this problem where you only have one-shot interactions, but those interactions are observable. And here we can have a really clear grounding of what reputation is. Your reputation is the population's beliefs about what type you are, right? So it's really closely tied now to a particular computational variable. All right, so here's what the results look like. On the x-axis, I'm varying the probability that an interaction will be observed by everybody. And you can see when it's observed by nobody ever, we're back to the one-shot game generator. No cooperation is possible. But as we make the observations more likely to be observed by everybody, we can get cooperation even in this one-shot setting, and we get high rates of payoff in that corresponds, right? The agents are actually cooperating with each other. Again, kind of showing some robustness to noise, but likewise that as your error rate grows, you need to have more observability. Again, should be intuitive. And then finally, this is a kind of observation error. This is a more challenging kind of error where, because this can create common knowledge failures, right? Unlike the action error, which is it's like a trembling hand, right? My hand slipped and I chose the wrong action, but we all saw what I did. So it doesn't mess up with the beliefs. Here, an observation error is trickier, right? Because it says, let's say, I played action one. I think I still played action one, but you thought I played action two. And so now our beliefs are going to diverge. So this is a much harder kind of error to deal with that had been studied in the literature. And we can see that, actually, it's all relative, right? But our models are actually relatively robust. Up to almost 10% error rate, you still get some amount of cooperation in the population. And this is, really the hardest case possible. Okay. So I showed you how the Bayesian reciprocator can kind of solve our problem of cooperation in the game generator. I see I've been going slow because I want everyone to catch everything, but so now I'm going to go a little bit faster because I do want to leave time for questions, and I'm happy to stay after too to talk more. But okay, so you're saying, okay, well, Max, look, you invented this like new world, and then you invented an agent, and of course it's going to do well there. Well, what happens if we take our model and take it back into like the classic world of evolutionary game theory, like the repeated prisoner's dilemma? How does it fare in that situation? So I don't have time to introduce all these different strategies. Just know these are like, each one of these is like multiple Nature papers, and they've been studied to death over the last 30 years. These are like the state of the art. Like these are like the baselines to beat in this world. And I'll just show you what happens. So what I'm showing you kind of two variables at a time. On the x-axis is the action error. On the y-axis is how many repetitions. And the color is going to correspond to what strategy was most abundant in the population, steady state at that time. So we're seeing kind of like what parameter regions enable different strategies to succeed. And first, I'm going to show you without the Bayesian reciprocator in play. So here you can see is, for this, there's this orange region where win, stay, lose, shift, WSLS, is the dominant or the most abundant strategy. Everywhere else, it's just all D. Red is selfish or all D, right? That's without the Bayesian reciprocator. Now, that's a simultaneous prisoner's dilemma. We both pick a cooperator defect on the same turn, and we observe it. Now, if you go to and then I'm also going to look at a second variable, which is benefit cost, like how valuable is cooperation? Then I look at the sequential prisoner's dilemma, right? So sequential prisoner's dilemma is very similar. It just says, I'm going to play cooperate, you observe, then you play whatever you want, defect, then we go back and forth rather than playing at the same time. And this is a well-known result. If you change the game just a little bit, now forgiver, this new automata is a dominant strategy, right? This is what I was saying in the very beginning. You change the game a little bit, a different little algorithm becomes dominant. Now let's add the Bayesian reciprocator into the game and see how these graphs change. So first of all, two things to notice. One is there's no other colors other than blue or red. So the Bayesian reciprocator outcompetes all of the automata strategies. And you can see that there's just more blue, right? The blue is bigger. There's cooperation is possible for a wider range of parameters. And you can see that unlike in the kind of baseline case, it's true for in both the sequential and simultaneous versions of the dilemma. So we get a much more robust kind of cooperation. We do this for all memory one strategies. And I'll just show, with the Bayesian reciprocator, you get the big black. Without, you get the small black, meaning there's a lot more cooperation happening when the Bayesian reciprocator is there. And we just show that the Bayesian reciprocator really is the main strategy. There's a few nice automata. Mostly it's these not nice defecting automata at the fringes of the parameter space. Okay. So I want to just kind of wrap up. We're kind of I was in some part inspired by this framework that Press and Dyson introduced in 2012, and this is a really cool paper if you haven't seen it. It's like two physicists came in and like basically using like linear algebra like discovered something about iterated prisoner's dilemma that no one had ever seen before. And they kind of in their framework though they characterize two types of players: an evolutionary player, which is like the tit for tat or these other strategies I've talked about. Or they hypothesize that there could exist a theory of mind-based player that infers the strategies of others. And they hypothesize that a player with theory of mind could resist the kind of extortion strategy that they had developed in their paper and other kinds of manipulative strategies, and concluded with this line that they kind of pose for future researchers. It is exactly evolution on the hugely larger canvas of DNA-based life that ultimately has produced X, the player with the mind. And I think, I hope that in some sense, we've kind of risen to that challenge and developed this player with a theory of mind and shown how valuable theory of mind can be for enabling cooperation to work between self-interested agents. All right, so just to kind of sum up, we introduced this Bayesian reciprocator, a new model for the emergence of cooperation, and it leverages theory of mind, and in fact, a recursive theory of mind for a distinct advantage in these games. We quantify the advantage that theory of mind enables in using evolutionary techniques from evolutionary game theory. And I think in some part it explains, at least I hope, why humans, the most sophisticated cooperators on the planet, also have the most sophisticated mental machinery for understanding the minds of others. And when you kind of look at the different setups we did here, right? Yes, we introduced a more complex environment, this game generator, but we also introduced, and yeah, so then we got a more sophisticated algorithm or strategy, this Bayesian reciprocator, which is has a lot more going on. But I hope that so the results show that it's not just more sophisticated problem needs a more sophisticated solution. We actually got a more powerful solution, right? We can go back into these simple scenarios and do even better than any of the simple strategies can do themselves. Okay, so I'm not going to spend any time on some upcoming work that might be interesting to others. You can kind of check what's coming out from our group. I will first thank the Cooperative AI Foundation both for funding my work and kind of helping me get a lab off the ground. And just plug here are some of the students who have been working with us. I'm taking PhD students through the computer science department this year at UW. So please apply through CSE if you're excited about any of these kinds of problems or cooperation broadly, cognitive science of cooperation, theory of mind, all very exciting areas for our lab. So with that, I'd love to take any questions. And yeah, I'm happy to stick around if there's interest.
Okay, fantastic. Thanks so much, Max. That was a great kind of overview of some of these things. And also I think actually for me as well, it's kind of useful to spend a little bit more time on some of those basics, especially that kind of theory of mind stuff that maybe some people in the audience a little bit maybe less familiar with if they come from more of a kind of conventional machine learning background and thought less about that stuff too. Um, so that's great. We definitely have at least 10 minutes for questions. We'll see if we can go maybe a little bit over if there are still things left to discuss. So just as a quick reminder, the thing I mentioned at the beginning of the call, if you have any questions, please just chuck them in the Q&A box, which should be at the bottom of your Zoom screen. Even if you don't have questions, you should upvote the ones that you want voted, because I'll basically just proceed down the list by picking the most upvoted ones. If it's been asked by a particular person and you have the ability to unmute, you're not in, say, like a library or in like a noisy place, then I'll hand over to you so you can ask your question. And if you can't unmute, then I'll just read out the questions. So first one we have is actually from an anonymous person anyway, so I'll read this out. So someone says, would love to hear more about, I think this is a remark you made, Max, during the talk, which is about how to scale belief updates via approximation. And this person says, more generally, I feel confused about how to apply these ideas from Bayesian theory of mind to build, instead of just reasoning about, generative AI agents. So yeah, I wondered if you could speak to that maybe.
Yeah, maybe two thoughts. I think these models are okay. So two thoughts. First, let me just take the second one first, which is how to scale these like relatively these are like Python based agents, right? At the end of the day, this is not like your large scale LLM. The first thing I'll say is I think we're already seeing evidence that many of these kind of like more broadly trained systems can do a kind of Bayesian inference in the way they are reasoning about different problems. We were starting to see that like meta learning type strategies can allow like large scale neural networks, for example, to approximate the distributions to Bayesian to these kinds of Bayesian approximation problem, or sorry, approximations to these Bayesian updates. So I would say that's like a really exciting area of open research, right? People have done this mostly in these non-social domains. And so I think there's an opportunity to look at cooperation, theory of mind, mental state modeling, using meta learning as a way of scaling these ideas. And what's nice is like by having kind of both the underlying kind of probabilistic Bayesian model and the neural, potentially more scalable model, you can kind of quickly check your results and go back and forth. So the Bayesian model might be useful and I should also say the Bayesian model might even be useful for training such a model, right? First off, then I would say then go to the first question is, how to actually scale this stuff, right? So I may have kind of, here, let me go to the slide. I think I do this in the talk just because there's not a lot of time, but there's something sort of hidden here, which is, yes, this like it scales, looks like it scales better, but it actually doesn't scale very well either. This is basically, if to do exactly, you have to basically have a representation for every subset of possible agents that have interacted with each other distinctly. So that's like basically in the limit of that, that's like the power set, and that is really bad, right? So but I don't think that's necessary, right? I think, we can kind of coarse grain this in ways that make more sense, where maybe it's like, yeah, I want to keep track of like what, all the dyadic interactions, maybe even the triadic, or, a little bit beyond that. But at a certain point, I don't need to know, well, agents A through D saw this, but not agent U. And like, I can just think like, yeah, we should just all know that. Like, if I can assume that you're from a certain, place, or have a certain kind of experience, that I should just assume you have the same knowledge that I have. Like, if you went to my high school, you should all know that, player W sucks or something like that, right? So I don't have to have the precise representation of every subset of every group. I think it'd be really interesting to see how far we can get by just as an initial step, just course grading some of these representations. And I think we can get way below the power set. But I haven't done that, and I think that could be a cool thing to look at. So that would be where I would start. As a more kind of like fuller project beyond that, I think, again, like looking at like how do we make those those types of generalizations, right? I give you the example of like, oh, well, we went to the same high school. I think there's also learning, a process of learning of like, how do you know who you can expect to have common knowledge with, right? And so it's going to be based on, probably not such sophisticated factors like shared experience, shared background, obviously shared observation, amount of time I spend with that person, things like that. So it'd be very cool to start to unpack what goes into that. And I think, oftentimes at least what I see, a lot of our failure modes interacting with, LLM like systems is this challenge of context, right? I have context that the system doesn't. But sometimes the system has more context than I think, and sometimes has less context than I think. And so ultimately you can think about some of these failures as a certain kind of common knowledge problem. And maybe there's ideas here that could actually help make progress on a problem like that. So ping me if you're interested.
Okay, great. Thanks. I'm going to keep rattling through these questions. And one currently at the top is from Chris Santos Lang. Chris, if you can unmute, I'll give you just a couple of seconds to do that. And if you can't, I'll assume that you can't, and we'll read out your question.
Hey,
Perfect.
yeah, I was just this idea of wanting to cooperate with people only who think like yourself reminds me of political polarization. So I'm thinking there may be some serious disadvantages to this in the long run, and I'm wondering whether you're exploring that and documenting that.
Yeah. No, that's great. I think one of the first things we learned in this project is we're like, wait, this sounds great, but it's actually like extremely parochial, right? It's like, you have to be one of us, otherwise I don't care. Like, just to be clear, right? The Bayesian reciprocator does not cooperate with the altruistic player. Now, maybe you think that's okay, right? Like, if someone's like, giving to the Red Cross, donating to ISIS, maybe you don't want to cooperate with them, right? Like, they're too broad. It's not the right thing. But I think what's different. So I think you're right, and I think this is not going to explain all of human or cooperation, certainly, and also not all of the kind of cooperation that we want to see. But it is a very robust form of cooperation, right? And in the sense that the thing that you're conditioning on is like me, but it's like me in a very specific way, that how it relates to cooperation. Now, I didn't say this, but it's important, I think, to note that you could take like me to be like me in every way. And the way I wrote the math is like, utility function equals my utility function. Well, if you like apples and I like oranges, does that mean then our utility functions don't match? That's not good, right? That's not the intent of what I'm talking about here. So I think, again, we would need to have to go beyond this kind of scoping. What actually is the conditionality for the reciprocity? I would say it's just the parts that are relevant to this kind of weighting each other's utility. Like, that's the part that matters. But I think, again, like a more formal and specific account of what should enter into that judgment and what doesn't is definitely needed and well worth thinking about.
Thank you.
Fab. Okay. Next one at the top of the list at the moment is from Andre. So if you can unmute, then go for it. And if not, I'll.
Yes,
okay,
thank you. So thanks, Max, for this nice research. I really love how elegantly it's done. So, and I probably continue what Chris said. So if agents become more and more good in theory and mind, as you stated at the beginning of your talk, it brings not only many benefits, but many risks. So I'm curious which risk you consider and which methods you see and propose how to mitigate them.
Yeah, great question. I mean, I think this comes up in some of the questions about personalization. This is how I'm going to at least take this question. I think in the context that I'm looking at in this very narrowly in this paper, I'm not sure there's a big risk of knowing too much or being able to learn too much. Although if you have an idea, please share. But I will say that over personalization can be kind of scary, right? We sometimes don't want AI systems that know everything about us, and they observe us clicking around on the web for an hour. They're like, oh, I build this whole behavioral profile about us, and we're like, whoa, I didn't realize I'm leaking so much information about who I am through my behavior. I think that can sometimes be somewhat scary, and so I think maybe taking your question to a little bit more of a human-like way is, when do we know not to use what we've learned about someone is a really interesting question that I don't know if there's much study on, right? I think we're always thinking about theory of mind is going to let me know you better and then do something better. But oftentimes it requires sometimes may require a certain kind of restraint. Like, I know something about you, but you might not want me to know that, and I'm gonna restrain from using that information. So don't have any particular example, but I mean, I'm sure we can all think of some that involve sensitive information about ourselves, things like that.
Yeah, I will probably write you a risk because I think a lot about that. One thing which worries me is that it's increased ability of models to manipulate people, and there are many bad actors, and they may teach the model to manipulate, like writing bad code and all these things. And for example, such actors as authoritarian regimes, they have access to a lot of personal data. They can have access to messengers, so they really can teach their models a lot about you. And if they're good in theory and mind, they can manipulate you very easy.
Yeah.
Okay.
Yeah. Great point. Yeah, persuasion, manipulation, obviously very key. I'm not of the belief that we can say, well, we shouldn't build that capability, because I think they're all going to happen. So I'm much more personally thinking about well, what do we do when they have those capabilities? Yeah, I'm happy to stick around, by the way, if there's more questions.
Okay, yeah, fantastic. I was just about to ask because we're at the hour, but I was also a bit slow to start. So as long as you don't have a hard stop, maybe I'll try and get through maybe 2 or 3 more questions if we
Sure.
can. That'd be great. Thanks. Yeah, we're not going to have a chance to get through all of them because there's a lot, but I'll proceed anyway. So the one currently at the top, again, an anonymous person. What are the main constraints on the game generator, i.e. what class of games can be output from the generator, and how do you think your results would change if those constraints were relaxed?
Yeah, the main constraint. So yeah, the main constraint on the game generator is that, at least relevant for cooperation type studies, is that we currently restrict to games that can be constructed in terms of agents acting individually. So something like an ultimatum game is fine, but games where agents have to act simultaneously and it can't be decomposed into 2 independent decisions, those we currently have not implemented. And I don't actually think there's a big issue there, but it required a little bit of a technical update in how we did the modeling, and so we didn't do it. But that would probably be the main thing I can think of.
Cool, nice. Thanks for clarifying.
I'll also just say, I think there's a lot of value in designing particular games that get at particular questions, and by kind of just saying, oh, here's a random distribution of a bunch of stuff, you're gonna just all of that, those interesting, is the centipede game in our distribution? I think so, but are we ever sampling it? Probably not, right? So, there's things like that.
Nice. Yeah, I thought it was an interesting methodology in general. And actually, maybe I can just ask a really quick follow-up question to this, which is how do you define that distribution over the kind of generative model that produces the games? Are there some kind of high-level principles that you use to try and do that? Or yeah.
We tried to at least give similar parameters that at least were familiar to people from prior work. You can control the average cost, the average benefit, so then you can map that back into what you would see in a social dilemma, number of actions, number of players. Those were the main things. Observability, noise. So we actually in many ways, it was very much trying to say, how do we go one step beyond what people have done going from the other direction of like, let's take, coin games and grid games and much more sophisticated sequential tasks and study them in an evolutionary context.
Cool, great, thanks. Just abusing my moderator's privilege there to ask that question, so thanks for entertaining that. Martin has the next question on the list. So Martin, if you're able to unmute, go for it. If not, I'll read it out. Thanks. Okay, I'm guessing Martin is not able to unmute, so I'll read it out, which is, how are the priors of the players initialized? So without posterior or new data observations available yet, are those initializations the assumption of whether the player is an altruistic or selfish character?
Yeah, good question. In the results I showed you, they all are initialized with 50% of the probability on Bayesian reciprocator, and the rest evenly spread across all of their types. In the supplement of the paper, there you can see results where we changed that assumption, and it has very little effect on the ultimate results. Basically, within the first couple interactions, you get so much information about what players are doing that it overwhelms the prior. But you do see some interesting behavior when the prior is really low, because in that situation, the Bayesian reciprocator expects other Bayesian reciprocators to defect on the first move. And so you get a kind of like initial like flip-flopping back and forth, but it actually, after a few rounds, ends up being cooperative quite quickly. So it's kind of cool, but cool that it's robust. I mean, I think a lot of that just relies on the convergence of Bayesian inference.
Nice, cool, makes sense. Okay, I think maybe we'll try and make this the last question because there's one that's just risen to the top here, which is again from an anonymous participant. But Max, I think one that you'll be especially well placed to answer given your background. So maybe this is a nice one to round off in, which is, can you point us to any research you might be aware of that uses these insights to help understand or explain our human society and or possibly how to design governance systems or other interventions to drive greater human cooperation?
Yeah, I mean, I think maybe multiple Nobel Prize worths of applied insights from this work. I'll point you to two places. One, if you're interested in like kind of the more like behavioral economics, like lab experiments of how things people have studied, Dave Rand has a really nice review paper called Human Cooperation in Trends in Cognitive Sciences. That'd be one place to start. Just a really great starting point for just reviewing kind of a couple decades of work. And then the second is more on the like taking it to real applications is I'm been really inspired by like Elinor Ostrom's work on governing the commons, and that's very much a applied version of these ideas in actual communities and studying the sophistication in which some of these ideas get embodied in institutions. I think you guys already had Jijing speak about our work on GovSim and cooperator collapse. So that actually might be for those kind of interested in those ideas in an AI perspective. This paper, Cooperator Collapse, that I did with Jijing Jin, is also a nice paper that kind of tries to do those in an LLM like setting and reviews at least a little bit of the work from like Elinor Ostrom that might be interesting to you. So I point you in both those directions. Thank you all.
Nice.
Yeah, it's been a great audience, great questions.
Excellent, yeah. And yeah, thanks again once more, Max, for excellent presentation and for your patience and yeah, answering all those questions. Thanks to everyone else in the audience as well. If you are not already on the mailing list for the Cooperative AI Foundation, you should sign up because you'll hear about all of these seminars coming up next. And yeah, I hope to see you all there at the next one. And yeah, thanks once again. Cheers.
Take care all.